Welcome to the lecture on rational exponents. A rational exponent is an exponent that has a fraction in it. And what we're going to define fractional exponents to be are radicals. So we're going to define a to the 1 over n to mean the nth root of a, the type of radical that we're taking. In the example of negative exponents, if you saw a to the negative 1 over n, just remember that a negative exponent flips you over or makes you become a reciprocal. So this would just be 1 over the nth root of a. So the denominator that you see in your fractional power becomes the index that we want to use on our radical. So for example, if I want 121 to the 1/2 power, because I see a fractional power, I know that I'm talking about a radical. Because the denominator is a 2, this implies a square root, and the base here that I'm using is 121. So this question is really the same as saying, what is the square root of 121? Now you can do this on a calculator, but hopefully you do have some of the common perfect squares memorized in your head, or you know them really well, because you'd want to be able to recognize that the square root of 121 is just 11. Okay? So if we saw 27 to the 1/3, another fractional power, so we want to use a radical, and the denominator here is a 3, so this is going to be a cube root, and the base is 27, so this question is really asking for the cube root of 27. So what number cubed gives me 27? The answer would be 3. The next example is really important because of this negative. Notice that there are no parentheses in the example, so this 1/2 power only gets associated with the 9. So only the 9 is being raised to the 1/2 power. The negative is just going to stay out front. Now a 1/2 becomes a square root, and since it was only the 9 being raised to the 1/2, only the 9 goes under the square root. Square root of 9 becomes 3, and the minus that was out front stays put, so our answer is -3. Now if you contrast that example with the next one does have parentheses. So that means we want to raise the negative and the 4 to the 1/2 power. So a 1/2 becomes a radical, and because the denominator is a 2, this is a square root. And under that radical we want a -4. So what's the square root of -4? And the answer there would be no solution, because we are not allowed to take the square root of negative numbers in the real number system. This does exist as a complex number or an imaginary number, but in this section of notes we're only going to be referring to real numbers, so this would not exist as a real number. In the next example, we have -32 raised to the 1/5, so both the negative and the 32 are going to go under the radical, and because the denominator is 5, this is asking for the 5th root of -32. Now, unlike the last example, you can do a negative under an odd root, and 5 is an odd number. So this does exist because the answer would just be -2, since -2 times -2 times -2 times -2 times -2 gives you a negative back, -32. So it's okay to have a negative under an odd root. It's not okay to have a negative under an even root. In the last example here, we have 81x to the 8th, all raised to the 1/4 power. So a 1/4 power is a radical, and because the denominator is 4, we want a 4th root. Underneath, we want 81x to the 8th. And in order to simplify this, we could break it up and do the 4th root of 81 times the 4th root of x to the 8th, and simplify each of those. So what number raised to the 4th gives you 81? And the answer to that would be 3. To simplify your variables, you're trying to see how many powers of x can I pull out. And since 4 goes into 8 twice, we're going to be able to pull out 2 powers of x. So we're going to have an x squared left over, and our final answer, 3x squared. Now what all of these last examples had in common was we had fractional powers with denominators that gave us radicals, but the numerators of all these powers were 1. So what do you do if the numerator is not 1? That's what we're going to talk about next. So if you see something like a to the n over m, what you want to remember is that denominator tells you the type of radical you should be doing. It's going to be the index of your radical. So if I see an m in the bottom, then I want to be using an mth root. The power on top becomes the power that you are raising this whole thing to. Now we can do this in two ways. We can raise just the a to the n, or we can raise the entire expression, the mth root of a, to the n. Sometimes it's more helpful to think of it this way, where you use that power of n on the inside of the radical, and sometimes it's more useful to do the mth root first and then the power. So which one should you use when? When you have variables involved in your base, then usually it's easier to do the power first and then do the root. If you only have constants for your base, if you only have numbers down in the bottom, then usually it's easier to do the radical first and then raise that answer to the power. So if we look at these next examples, they all have just numbers in the base, 64, negative 32, negative 36. So in this case, we're going to want to use and think of a to the n over m as the mth root of a, figure that radical out first, and then raise that answer to the nth power. And this is what we want to use because a is a constant down below. So let's try it out. If we see 64 to the 3/2, first let me just show you the two ways you could write this. Your two options would be to do a square root, because this is a 2 in the denominator, and you can either do the square root of the 64 and then cube that whole answer, which is what we're going to do. We're going to use parentheses here because the base is a number. The other option is you could cube the 64 first and then do that square root. Why wouldn't we want to do it this way? Because 64 cubed is going to get very, very large, and then trying to figure out what the square root of that answer is just becomes very hard to manage. So in this case, it's much easier to figure out what the square root of 64 is first, because that number is small, and then cube that answer. So what is the square root of 64? It's just 8. And 8 cubed, you could figure that out on your calculator. You just do 8, and you press your caret key to the third power. So this is 512. So our final answer is 512. In the next example, remember that idea about parentheses or no parentheses. This does not have parentheses. So the minus stays on the outside, and only the 32 is going to go under that radical, and only the 32 gets raised to the 2/5 power. Because it's a 5 in the denominator, we want a 5th root. Because this base is 32, a number, it's easier to figure out what the 5th root of 32 is first, and then raise that answer to the 2nd power. So what is the 5th root of 32? What number to the 5th power gives you 32? That's 2. Then we want to square that, and remember that minus sign is going to be the very last thing we do. That's on the outside. So you're just squaring a positive 2, which turns into 4, and the minus stays out front. So our final answer is negative 4. In this last example, there is parentheses, so when we do our square root, we're doing the square root of the negative and the 36. We want to figure out what that is first, and then raise all of that to the 3rd power. But remember what we said earlier, you're not allowed to take an even root, like a square root, of a negative number. So this doesn't exist, so we are going to have no solution. Okay? In the next example, now we have a negative exponent. So to talk about that again, remember that negative exponents cause you to take reciprocals. They flip you over. So the first thing you would want to do here is take this 81 to the negative 3/2 and flip it over to the denominator. So I'm going to put it underneath a 1, and now this becomes 81 to the positive 3/2. So once you do that flip, or do that reciprocal, the exponent becomes positive. And you want to take care of that first. Take care of that negative exponent first before you start simplifying what's left over. So now let's simplify. We're going to leave that 1 on top. Because there's a 2 in the denominator, this means a square root. I'm going to do the square root first and then take that answer to the third power. Well, what's the square root of 81? We know that that's 9. So then we just need to figure out what 9 cubed is. So 9 to the third power gives me 729. So this answer is 1 over 729. Now on the next example, we have a negative exponent again, but notice what we have inside to begin with. We have a fraction already. So there's kind of a shortcut here that you can do. If you have a negative exponent, which means take a reciprocal, what we can do is change that exponent to a positive 2/3, and we can take the reciprocal of the original fraction. So I'm going to flip over this fraction and make it 125 over 64. Now that negative should still be inside the parentheses. It doesn't really matter whether you put it out front like I did, if you put it in the top or put it in the bottom. You just want to make sure that it's there somewhere. So now that we've taken care of the negative exponent, then we can go ahead and start simplifying this power. Because there's a 3 in the denominator, that means a cube root. And we're taking the cube root of negative 125 over 64. You want to figure out what that cube root is first while the numbers are still relatively small, and then square that answer. So what number cubed gives you 125? That would be 5. What number cubed gives you 64? That would be 4. And the negative is going to stay put since the cube root of a negative stays negative. So the cube root of negative 125 over 64 is negative 5/4, but we still need to square that answer. So our final answer, when you square a negative, it goes away. The 5 squared becomes 25, and 4 squared becomes 16. So our final answer is positive 25/16. Alright, so all of these examples that we just worked on had constants in the base, numbers in the base. And so if that's the case, usually you want to do the radical first and then raise that answer to a power. In the next few examples, we have variables in our base, 3p, 5y, z, x. So here we want to do the power first usually and then take the radical of that answer. So here we're going to be using the alternative form. If we see a to the n over m, we're going to want to do the mth root of a to the n. So the power should be on the inside of that radical. Figure out what that is first and then take your root. So for example, if I have 3p to the 3/4, we're going to use this because the base has variables. We have a p involved. So if we rewrite it, this is going to be the 4th root, because we have a 4 in our denominator, of that whole base 3p raised to that 3rd power. So this time I'm putting that cube on the inside of the radical. Then to simplify this, we just have to cube out 3 and p. 3 cubed is 27, and p cubed stays p cubed. And this can't be simplified because 27 is not a perfect fourth, and it doesn't have any factors which are perfect fourths, and p cubed can't be reduced because I would need to have at least 4 p's before I could pull any out. So this is a reduced answer. Okay, on the next one we're going to do the same thing, but we have a negative exponent to deal with first. So first you want to deal with that by flipping this whole expression over and putting it under a 1, and that makes this exponent on the 5y become a positive 3/5. Now if I reduce this, we're going to want to take that 5, which is in the denominator of our power, and make that a radical. So this is going to be a 5th root. And because we've got variables, this y showing up, we're going to want to keep that cube on the inside of your radical. So let's go ahead and figure out what this is. We want to cube the 5 and the y. So 5 cubed is 125, and y cubed stays y cubed. And this doesn't reduce because I don't have enough y's to pull any out, and 125 is not a perfect fifth. So we just leave our answer like that. You might be asked to rationalize a denominator here. That's up to your instructor. Okay, next example. Z to the 3 halves. So this time, again, our base is a variable. So when I do my radical, I want a square root here. And the z is going to go underneath, and then the power on top was a 3, so I'm going to put that power underneath my radical, so this becomes the square root of z cubed. Now this can be reduced, because remember, this is a square root. I have 3 z's, I only need 2 to be able to pull one out. So if you want to do this kind of the long way, this is like saying we're breaking up z cubed into a z squared and 1z left over. The square root and the square cancel out, giving me a z on the outside, and the square root of z that was left over just stays put. So our answer is z squared of z. As an alternative, you can just divide 2 into 3. 2 goes into 3 once, so we get 1z on the outside. And when I divide 2 into 3, there's also a remainder of 1, so there's 1z underneath as well. So that's why we get 1 outside and 1 inside. For this last example, parentheses again are an issue here. We don't have any. So that means this 1/2 power only gets associated with the x. The 3 is just going to stay out front. So x to the 1/2, a 1/2 power becomes a square root. So this is going to be 3 square root of x. And that can't be reduced any further. So there's our final answer. Okay, in the next few examples here, we're going to use the fact that rational exponents can sometimes help us reduce problems, because rational exponents are fractions, and sometimes you can reduce fractions. So for example, if I have the square root of 5 to the 10th, if we rewrite this as fractional powers, we might be able to do some reducing. So we're going to rewrite using fractional powers, and then we're going to reduce the fractions. So if I have a square root, so the index here is a 2, and 5 to the 10th, the base is 5, and this is going to be a fractional power. The denominator of the fraction is the index, which was our 2, and the numerator is the power that we see, which is this 10. And since 10 divided by 2 reduces, this just becomes 5 to the 5th. You could leave it like that, or you can figure out what 5 to the 5th is, and we get 3,125. So there's our simplified answer. On the next example, do the same thing. You really don't want to have to take 6, raise it to the 8th power, and then try and figure out what the 4th root of that is. Instead, you can just think of this as 6 as the base, and then the denominator is the index, which is 4, and the numerator of the power is the 8 that's on the inside. And 8 divided by 4 just reduces to 2, so all of this just becomes 6 squared, and we know that that's 36. So it's much easier to use those fractional powers, reduce them first, to get a much simplified answer. And then you don't have to deal with really, really large numbers. Okay, the last one here, we have the cube root of x squared. So if we wanted to rewrite this, this would become x as your base. The denominator is the index we're taking, and this was a cube root, so I want a 3 in my bottom, and then the power on top is going to be that square. X to the 2/3, we can't really do much with that because we don't know what x is, so that's our final answer. Okay, on the next examples, again we're going to use the fractional powers to help us simplify these expressions. And here we are also using laws of exponents to help us simplify. So in this first example, we have 6 to the 4/3 times 6 to the 2/3. Remember your law of exponents that says if you have two things with the same base that you're multiplying, then you get to add the exponents. So the base is going to stay 6, and 4/3 plus 2/3 becomes 6/3. 6/3 can be reduced to 2, and 6 squared we know is just 36. So it's much easier to work with those fractions, simplify to get our final answer. Same idea on the next one. The bases here are both 64, so they match. This time we're dividing our bases, so the law of exponent that applies here is when you are dividing common bases, you can subtract the powers. And we want to do the top power minus the bottom power. So this would become 64, that base stays put. The top power is 5/3 minus the bottom power 1/3, and 5/3 minus 4/3, 5/3 minus 1/3 gives us 4/3. And we don't want to stop there because we want to see if that can be reduced. So change it into a radical to see if you can reduce. The denominator here is a 3, so that means we have a cube root. Because this base is a number, just 64, it's easier to figure out what the cube root is first and then raise that answer to the 4th power. If you try to put the 4th power on the inside, then you have to figure out what 64 to the 4th is, and that's going to be a really big number to work with. So take the cube root first. Cube root of 64, that's just 4. So all we need to know is what 4 to the 4th is, and if we do 4 to the 4th, we get 256. So this whole thing reduces to 256. Okay, the next two examples have variable bases, but they match. So this is r and base r, so we can still use those laws of exponents. If you're multiplying the bases, then you get to add the exponents. So the base stays r, negative 8/9 plus 17/9 is 9/9, and 9/9 just becomes 1. And if you have r to the 1, you don't even have to write that 1 up there, it's implied. So our answer is just r. Now for the next example, we have 3 z terms. You can do this many, many different ways. I'm just going to show you one way. If you have all these different z's, you want to probably combine together these bottom two first before you deal with that fraction. That's just one option, but that's the way that I'm going to show you. In order to combine these two, we're multiplying the bases, so we're supposed to be able to add their powers. Unfortunately, I can't add 5/4 and -2 unless I get a common denominator. So I'm going to leave the numerator alone for now, and let's just change our -2 into a new fraction with a denominator of 4. It's going to stay negative, and right now this 2 is over a 1, so if I multiply the top and the bottom by 4, then -2 should be the same as -8/4. Now that I have a common denominator, we can add these two bottom powers together. 5/4 plus -8/4 becomes -3/4. And here again you have a couple of different options for you. Because I see a negative exponent, a lot of times when I see negative exponents, I automatically flip those. So since this negative exponent term is on the bottom, it's going to flip up to the top. So the z to the 3/4 that I already had in the top stays put. And then this z to the -3/4 moves up, and the exponent turns positive. So we get another z to the 3/4 next to the one we already had. Now to simplify these two z's, again we're multiplying the bases, so we should be able to add the exponents. 3/4 plus 3/4 is 6/4, and if we reduce that, that becomes 3/2. Now your question here might be, should I write this as a radical or not? As a radical, it would be a square root, and then the z cubed would be on the inside. You could do it either way. Usually my rule of thumb is if the original problem starts with rational exponents, then it's okay to leave your answer with a rational exponent unless the directions tell you otherwise. So in this problem, I think it's fine to leave your answer as z to the 3/2. Okay, last example of this type, we have just more complicated stuff going on. We also have parentheses. So the first thing you're going to want to do is probably get rid of those parentheses, and we do that by distributing our powers across these multiplications between the a's and the b's. So we're going to take this -1/4 and distribute it to the a's and the b's, and then we're going to take the 1/6 and distribute it across. Now, since we already have powers on the inside, this becomes a power raised to a power, and the law of exponent that applies there is multiplication. So on the top, we're going to have that base a, and 2 times negative 1/4, do a little scratch work if you need to, is negative 2/4, which reduces to negative 1/2. So this becomes a to the negative 1/2. b has a power of 5, or 5 over 1. When I multiply that by negative 1/4, top times top over bottom times bottom gives me a power of negative 5/4. In the denominator, multiplying powers again, negative 3, or negative 3 over 1, times 1/6. We can reduce here a little bit. 3 goes into 6 twice, so this is going to leave me with a negative 1/2 power. And for 2, or 2 over 1 times 1/6, 2 goes into 6 3 times, so the power on b is going to be 1/3. Now, before you start moving things around and flipping things because you see some negative exponents, use a shortcut here. Notice something about these a's. They are a to the negative 1/2 on top and a to the negative 1/2 on bottom. Those are exactly the same terms. If you have one on top and one on bottom, they're going to cancel each other out. So we can just cross those off and we don't have to worry about them. Then in our next step, I do have a negative exponent on this b term, so that can flip down to the denominator. Since nothing's going to be left on top once I move that b, there's just going to be a factor of 1 left over, and that b to the 5/4 goes to the bottom, and it's going to join the b to the 1/3 that was already there. Now, in order to combine these, we want to multiply the bases, so we're supposed to add the exponents. Because I want to add 1/3 plus 5/4, I can't do that unless I have common denominators, since these are fractions. So if I have a denominator of 3 and a denominator of 4, the common denominator should be 12. So let's change these powers, or these fractions, to denominators of 12. Though 1/3, I need a 3 times 4 to get to 12, so I need a 1 times 4, so 1/3 is the same as 4/12. To go from 5/4 to a denominator of 12, I need to multiply the bottom by 3, so I have to multiply the top by 3. 5 times 3 makes this 15. So now I can add 4/12 plus 15/12 is 19/12. This is a perfectly acceptable answer. If your instructor doesn't mind negative exponents, this would also be equivalent to flipping it back up to the top and making it a negative 19/12 power. And as I said earlier, since the original problem had fractional exponents in it, I think it's okay to leave your answer with fractional exponents. However, if you wanted to change this to radicals, then you could, and I would do it for this version here where we had the 1 and we had our positive exponent, and this would just become 1 over the 12th root of b to the 19th. And there's more degrees of simplifying that you could do with that. So in this respect, I think it's easier and acceptable to leave it as a fractional power. Okay, the next couple problems that we're going to do are just some multiplication problems, getting used to these rational exponents a little bit more. In this first problem here, all we're really doing is distributing. We want to distribute this r power to this r power and this one to here. And remember that when you multiply a base r times another base r, you're supposed to be adding these exponents together. Unfortunately, since they're fractions, we kind of need to get some common denominators before we're going to be able to do that. So to make your life easier, look at all the denominators and think about what your common denominator would be. Since 2 goes into 4, then my least common denominator should be just the 4 times 5, or 20. So let's change all these denominators to 20s. So I'm just going to rewrite the problem so that all these have a fractional power where the denominator is a 20, and we have to figure out what these new tops are going to be. To go from 5 to 20, I would have to multiply by 4s on top and bottom, so 4 times 3 makes this new top 12. To go from a half to 20, I'd have to multiply by 10, so do that on the top. 1 times 10 is 10. And to go from 4 to 20, I'd have to multiply by 5, so 3 times 5 makes this numerator 15. Now when I distribute this times this, all I have to do is add these two powers together. So 12 twentieths plus 10 twentieths becomes 22 twentieths. So that's the first term. Then we're going to have our plus, and now we want to distribute this r times the second r, again adding exponents. So 12 twentieths plus 15 twentieths gives me 27 twentieths. Now you do want to reduce any of these fractions if you can. 22 twentieths does reduce to 11 tenths, and 27 twentieths does not have any common factors, so that's reduced. And you can just leave your answer like that because the original problem had rational exponents. Okay, the next example is the same way, and it's actually a little bit easier because if you notice all these fractional powers, they already have the same denominator, so I don't even have to worry about that. So we are just going to want to take this 4m to the 5/3 and multiply it by this first m. The 4 is just going to stay out front, and when I add these two powers together, 5/3 plus a negative 2/3 becomes 3/3. Then I'm going to bring down my minus sign, and now 4m to the 5/3 times 4m to the negative 5/3, the 4's get multiplied. 4 times 4 is 16. And for the m's, when I add those powers, 5/3 plus negative 5/3 is 0. Now we want to clean this up a little bit. 3/3 is 1, so this is like 4m to the 1, or you don't even need to write the 1 there. It's implied to be there. What is m to the 0? You want to remember this law of exponent that says anything to the 0 power is going to simplify to 1. So this is just 16 times 1, or 16. So here's our final answer. All of this turned into just 4m minus 16. Okay, so these were multiplication problems. The next two examples are going in reverse. Now we're going to factor. Whenever you factor, remember that you always want to factor out the smallest power of your common variable. So factor out always the smallest power that they have in common. So for example, if I have 3x to the negative 1/2 plus 15x to the 1/2, I'm going to factor out my GCF, my greatest common factor. We know that 3 goes into 3 and 15, so I know I should be able to pull out a 3. And both of these terms have x's in them. So here's where you want to make sure you take out the smallest power. So if I have a power of negative 1/2 and positive 1/2, the smaller power is the negative 1/2. So that's my GCF, 3x to the negative 1/2. When we factor that out, you're going to want to put parentheses, and inside the parentheses is what should be left over. From this first term, I pulled out the 3, and I pulled out the x to the negative 1/2, so there's nothing left here. Don't write a 0, however, write a factor of 1, because remember, we should be able to redistribute back to get back the original term. If you put a 0 here, 0 times anything is going to make that go to 0, and we don't have a 0 right here. We have the original term back, so it has to be a factor of 1 left over. Then we have our plus sign. Now if we go to this term, I pulled out 3, so we need a 3 times a 5 to get back to that 15. And I pulled out some x's, but not exactly the same amount of x's, so there's going to be some x's left over. Now this is kind of tricky. You have to kind of think backwards. How many x's do I have left? I'm going to put a little question mark here. Negative 1/2 plus what would get me back to a 1/2 power? So negative 1/2 plus what gets me to a 1/2? If you can't think that through, then just solve this like an equation. If you were to add 1/2, then what's missing here is a 1/2 plus a 1/2, which is 1. So in other words, we need to have an x to the first right here, so that if I were to redistribute back x to the negative 1/2 times x to the 1, adding those powers, negative 1/2 plus 1 does get me back to a positive 1/2 power. So we got it right. So here's my final answer. 3x to the negative 1/2, parentheses, 1 plus 5x. Okay, let's try that again. On the next example, again, we want to factor out a GCF. So are there any numbers that go both into 9 and 6? We know that 3 does. So I know I can pull out a 3. Then when I look at these two terms, they both have some k's. So I should be able to pull out some k's. What power should I pull out? It needs to be the smallest one. So which is smaller, negative 3/4 or negative 1/4? The answer would be negative 3/4 because it's more negative. It's more to the left on a number line. So that's your GCF. In parentheses, we want to write what's left over. So from this first term, I pulled out only a 3, so I need to have a factor of 3 left to get to 9. And I pulled out all of these k's, so there's nothing left but that 3. Then we have our plus sign. For the second term here, I pulled out a 3, but I had 6, so I have a factor of 2 left, and I do have some k's left over because I didn't pull out the same amount of k's. So there should be some k's left. How many are left? Kind of think backwards here again. I'm going to put that question mark in there again. Whatever power you pulled out, plus the power that we need to have here, should add back to the original power of negative 1/4. So negative 3/4 plus what gets me back to negative 1/4. If you can't do that in your head, then just treat it like an equation that you would solve. For the question mark here, I would add 3/4 to both sides. Negative 1/4 plus 3/4 is 2/4, which reduces to a 1/2. So the missing power is a 1/2 power. So negative 3/4 plus a half gets me back to negative 1/4. So our final answer is going to be 3k to the negative 3/4, parentheses, 3 plus 2k to the 1/2. Okay, so whenever you're factoring, always pull out the smaller of the powers, and when you're double checking, make sure that whatever you pull out times whatever left over, when you add those exponents, it should get you back to the original power. Okay, in the next few examples, we want to simplify these radicals. And the trick to these is like something we did earlier, where to simplify these, it's sometimes easier to convert your radical into a rational exponent first so that you can reduce that fraction and then turn it back into a radical. So here we're going to convert to rational exponents, which are those fractions. Then we're going to reduce, and then we're going to convert back to radicals. So for example, if I have the 9th root of x cubed, remember how we write this as a fractional power. The base is x, the fraction denominator is the index, so we want a 9 in the bottom. The power on the inside is your numerator. So x to the 3/9 can be reduced because 3/9 reduces to 1/3. Now, since this original problem started as a radical, we want to write our answer as a radical. Remember, you want to be consistent. So x to the 1/3 isn't a radical yet. What radical should it be? Well, the denominator here is a cube, so we want a cube root, and there's no power on top except 1, so it's just the cube root of x. So the reduced radical here is the cube root of x. Now on this next one, it's kind of tricky. This one you want to be a little bit creative on. When you first think of the 4th root of 36, you may think, well, 36 isn't a perfect fourth, and it doesn't have any perfect fourths in it. So how do we simplify this? Well, 36 should strike you as one of those perfect squares. So what you want to do is think of 36 instead as 6 squared. So this problem becomes the 4th root of 6 squared. The reason you want to think of that is because now that we have a power on the inside, we can create a rational exponent out of these two powers. This is going to be a base of 6. The index was 4 on that radical, so that's your denominator, and the power on that 6 was a 2, and 2/4 reduces to a 1/2, and a 1/2 converts back into a square root. So the 4th root of 36 turns out to be the same as the square root of 6. And you won't see that unless you think of that 36 as 6 squared instead. So that's another reason why it's really good to have those perfect squares and perfect cubes memorized, so that you'll be able to pick up on how to rewrite some of these problems so that you can reduce them more easily. Okay, here's another example just like that. We have the 8th root of 4y squared. 4 is not a perfect eighth, and y squared, there's not enough y's there to pull any out. So you may think, well, I can't reduce this at all. But actually we can, because 4 is one of those perfect squares, so you want to think of that instead as a 2 squared. So if we rewrite this as the 8th root of 2 squared y squared, then I have powers on the inside and an index on the outside, so we can change this to a fractional power. 2 is the base, the index was 8, so that's your denominator, and the power of 2 on the inside goes to the numerator. Then we do the same thing for the y's. Y is the base, 8 is the denominator, and the power of 2 on the inside is your numerator. 2/8 reduces to 1/4 for both of these fractions. And now I can convert both of these back into radicals. They both have the same 1/4 power, and since 4 is in the denominator, that can become a 4th root, and what would be left is 2 to the first, or just 2, and y to the first, which is just y, so the final reduced radical is the 4th root of 2y. Okay? On the next example, right away, we can rewrite these as fractional powers because we have powers on the inside and our index on the outside. So this y becomes power of 6 on top, 9 on bottom, and the z has a fractional power with a 3 on top and the 9 on the bottom. Both of these two fractions can be reduced. So 6/9 reduces to 2/3. 3/9 reduces to 1/3. Since these two denominators match, they're both 3's, then we can convert this back into a cube root, and under the cube root, we're just going to take the y squared and the z to the 1. So we're just taking that numerator power and attaching it to our variables. So our final answer, cube root of y squared z. And there's our simplified radical. Okay, on the next set of problems here, we're going to just take a look at a quick review of some properties that we've already talked about when we talked about radicals. These are multiplication and division rules, and basically they say that if you have the same index on both of your radicals and you're multiplying them, then you can consolidate this into a single nth root and just multiply the numbers underneath. So for example, if I have the cube root of 10 times the cube root of 50, since these are both cube roots, I can make this cube root of 10 times 50, and 10 times 50 we know is just 500. And then if you want to try to reduce that, you can. Are there any perfect cubes that go into this? Well, we know that 5 cubed is 125, so if you try that out, 500, is that divisible by 125? It does go in evenly. So that means we could break this up into the cube root of 125 times the cube root of 4, since 125 times 4 is that 500, and this reduces to 5. And the cube root of 4 stays put. So here's my reduced answer. Okay, so remember to always double check your numbers under your radicals to see if there are any perfect squares or perfect cubes that could be pulled out, and this one there was. For our second example here, now we have division involved, and there's a similar rule like the one we just did. If you have the nth root of x over the nth root of y, they're both nth roots, you can consolidate this and just divide what's on the inside first and then do the radical. And sometimes that's easier because it lets you cancel some things out. So for example here, if I consolidate this into a fourth root, one great big fourth root, and make a big fraction on the inside with the xy squared on top and the xy on the bottom, that's good for me because I can see that these x's are going to cancel out and the y in the bottom is going to cancel with one of the y's on top, so all we'll have left is just this one leftover y. And there's my reduced answer. Okay? Now what do you do if you have unlike indices? So these are a little bit more complicated. If I have the cube root of y squared times the sixth root of y, we can't multiply y squared times y because we don't have the same type of index for our radicals. They don't match. So we can't apply the rule that we were just talking about. So the only way to deal with these is to kind of do them like we did the other problems, convert to rational exponents first. So change these radicals into fractional powers, then you reduce and combine any way that you can, and then you convert back to radicals. So in this example, if I have the cube root of y squared, change that to the fractional power 2/3. And if I have the sixth root of y, change that to the 1/6. Now I still can't multiply these yet because in order to multiply the two common bases of y times y, we would have to add exponents, but I don't have like denominators. So here we're going to have to get common denominators first. So that would be a common denominator of 6. The 1/6 power already has the right denominator. To change 2/3 into a power of 6, denominator of 6, we'd have to multiply by 2's. So this new top is going to be 4/6. And now that the denominators are the same, I can add these together, and that would give me y to the 5/6. Now you want to be consistent. The original problem had radicals in it, so you want to make sure your answer has radicals in it. So don't stop here. Now we have to change this back into a radical. The denominator is a 6, so this becomes a sixth root, and the power 5 goes underneath because our base is a variable. So this is the same as sixth root of y to the 5th. Okay? In the next example, we're going to do the same thing. I'm not allowed to cancel out these two a's because the indices here are different. So what I have to do is change these into fractional powers. Fourth root of a becomes a to the 1/4. Fifth root of a becomes a to the 1/5. Now my law of exponents says that if I have two bases that match and we're dividing them, you're supposed to be able to subtract these two powers. Unfortunately, we can't subtract 1/4 minus 1/5 until we get a common denominator again. So in a lot of these problems, you're going to have to get common denominators. So let's do that. The common denominator here should be 20. 4 times 5. So to go from 4 to 20, I have to multiply by 5's. So this is going to be 5/20. To go from 5 to 20, I have to multiply by 4's. So this is going to be 4/20. And now that I have my common denominator, I should be able to subtract the top power minus the bottom power. 5/20 minus 4/20 is 1/20. Then don't stop there. Remember, if you start with radicals, you want to end with radicals. So we need to change a to the 1/20 into a radical. The denominator is a 20, so this is going to be a 20th root of a to the first power, or just a. So this is the 20th root of a. Okay? Next example, same exact thing. Fifth root of b squared over 10th root of b cubed. I can't try to reduce the b squared and the b cubed because my two indices here do not match. So we have to change these into rational or fractional powers first. So fifth root of b squared becomes b to the 2 over 5. The 5 goes in the bottom because it's the index. The 2 goes on the top because it's the power. In the denominator, 10th root of b cubed becomes b to the 3/10. Because the b's are on different levels, we're supposed to subtract the two powers, top minus bottom. We can't do that yet because we don't have a common denominator. So let's change these powers to denominator of 10. The bottom denominator power already had that 10, so that's going to stay 3/10. But the top one had a 5, so I'm going to have to multiply by some 2's. 2 times 2 makes this new power on top 4/10. So now that I have the same denominator, I can subtract. 4/10 minus 3/10 is 1/10. So this is going to be b to the 1/10. And remember, if you start with radicals, end with radicals. So if we change this back into a radical, the 10 is in the bottom, so it's a 10th root of b to the first, or just 10th root of b. Okay, the last example here is a little bit tougher than the others, and we'll see why in just a moment. We don't have common indices. We have a cube root, and here we have a square root, so you're not able to multiply 5 times 2 and get 10. It doesn't work that way. So we have to we have to change these into fractional powers first before we can multiply. So cube root of 5 turns into a 5 to the 1/3. Square root of 2 becomes 2 to the 1/2. There were no powers inside, so that's why these numerators are going to stay 1. Now here's the difficulty. Unlike the last 3 examples we did, we can't just add 1/3 plus 1/2 because the two bases aren't even the same. We don't have both 2's or both 5's here. They're different bases. So no law of exponents is going to enable me to combine these together. But we can still make this work, and we can still do it by getting a common denominator up here. And let's see why this is going to work for us. If we change these fractions to denominators of 6, then 1/3 times some 2's gives me 2/6, and 1/2 times some 3's gives me 3/6. Now that still doesn't enable me to add these. I can't do 2/6 plus 3/6 and get 5/6 because the bases don't match. The good thing about having the common denominator, however, is because they both match, that means I can change this into a 6th root. Remember, your denominator is the index of your radical. What's going to be underneath will be the 5 raised to that 2nd power, and this 2 raised to the 3rd power. So I'm not able to add 2/6 plus 3/6, but I can pull out that 1/6 power as the radical and then be left with the 5 squared and the 2 cubed. And those I can deal with because what's 5 squared? We know that that's 25, and 2 cubed, we know that that's 8, and if we do 25 times 8, then we get under our radical the 6th root of 200. And that is our new simplified radical. We took 2 different indexed radicals and turned it into one radical. So that's why it's considered reduced. Okay? Alright, the very last thing that we're going to do is work with our calculator just a little bit. I just want to show you how to evaluate some of these rational exponents on your calculator. Now I am demonstrating with a TI-84. However, you may not have a TI graphing calculator like mine. If you just have a scientific calculator, you're going to want to look for similar keys to the ones I have, and the order in which you input your numbers may be a little bit different than the way that I do it. You're going to have to experiment with your own calculator to figure out what works best so that you get the same answer that I do. So if I want the square root of 6,825, most calculators, or all scientific calculators, usually always have a built-in square root key. And you can see that here. It's right above my x squared button in blue. So what I have to do on my calculator is hit second x squared to see that square root button show up. On my calculator, it also automatically puts in a parentheses. Not all calculators do that. In this particular example, it's not a big deal if you don't use parentheses, but if you had to take a square root of a bunch of things added or subtracted, then you would want to use parentheses. So here, all I have to type in is 6825. If you want to be really careful about it, you can close the parentheses using the right parentheses button. But if you didn't do that and you just hit enter, it would still work. It still would give you 82.6135 and so on. Now when you're giving your answer, usually your instructor will tell you how many decimal places to give. It's usually pretty safe to give at least 2 or 3. So on this, if I round to 3, since after this 3, the next digit over is a 5, that means I should round up. So this would be 82.614. Okay? Now for a fractional power like 7/8, calculators don't have a 7/8 button, so you're going to have to use your power key, which on my calculator looks like this little caret button, this little sort of top of an arrow. So what I want to do here is type in the base first, which was 80, and then I'm going to type in that little power button, and I want to raise 80 to the 7/8. Now don't type in 7 divided by 8. That's going to give you the wrong answer, because if you make the calculator do this, it's going to raise 80 to the 7th power, which is going to be a huge number, and then it's going to divide that by 8. Okay, and this is 2.6 times 10 to the 12th, so you've got like 12 zeros after this number, so this is really, really large. So that's not what we want to do. What we want to do is press 80, raise it to the fraction 7/8, and here you must use parentheses. Your scientific calculator should have parentheses buttons, so look for those, and you're just going to do parentheses 7 divided by 8, close the parentheses, and now we're raising 80 to this fractional power, and it gives me 46.2597. If we wanted to round this up to 3 decimal places, where that 9 is, the next digit over is a 7, so we're supposed to round up. How do you round up a 9? Well, it's actually going to round up the 5 in front of it to a 6. So this is going to be 46.260 if you want to use 3 decimal places. Okay, negative cube root of 13. For this, we want to, I'm going to show you a couple different options. If you wanted to use fractional powers, remember that a cube root, let me go back over here for a moment, a cube root is the same as a 1/3 power. So you could do 13 to the 1/3, and that negative is on the outside. So here you would not be wanting to use parentheses. So for example, you could do the negative, and then just do 13 raised to parentheses the 1/3 power, and that would give you your answer. As another option, some calculators have a built-in cube root key. On a graphing calculator like mine, you have to use the math button to get at that. So for example, if I press math, here it is in number 4, this cube root with that little radical symbol. So I could press number 4 here, and it would do the cube root, and then I would type in 13, and that would give me my answer. I didn't type in my negative beforehand, so I would have to remember that that should still be there. So my answer rounded to 3 decimal places should be negative 2.351. Whoops, 0.351. So there's a couple different options for how you want to do a cube root. You can do a 1/3 power, or you can use the built-in cube root key. For the last example here, we do have a negative exponent. You could flip it over, or you can just make the calculator do this whole calculation. So how you would do that is you would type in your base first, 104, press your caret button, and then we want parentheses, because in the parentheses we want this whole negative fraction. So I'm going to type my negative button, 4 divided by 5, close the parentheses. So here's 104 raised to the negative 4/5, which is exactly what we're trying to find. Hit enter, and my answer is going to be 0.024 if I round to 3 decimal places. So play around with your own calculator. Make sure that you're used to how the buttons work and in what order you need to press things. Sometimes some calculators require that you type the power first and then the base. Some require the base first and then the power. So play around with what you have and ask your instructor if you have any questions. Alright, that concludes our notes on rational exponents. Good luck.